Alright guys, welcome back to Underground Science, and in this video we'll be looking at an example of calculating the pH value using an ice table. Alright, so we'll look at more examples in our future videos, but in this video we'll be going over one example of a weak acid, and we'll see how we can use ice tables, or an ice table in this video, right, to figure out the pH of a weak acid solution, of an aqueous weak acid solution. So let's go and get started. So let's read the problem. So we have a 1.49 molar solution of aqueous hydrofluoric acid. So hydrofluoric acid, turns out, is a weak acid. All right, so hydrofluoric acid is a weak acid. So it's good to keep that in mind, as we'll see later. All right, so we have a 1.49 molar solution of aqueous hydrofluoric acid. What is the pH of our 1.49 molar solution of our aqueous hydrofluoric acid? So let's go and try to solve this out. So first, we should write our aqueous equation, right? So we should write our hydrofluoric acid reacting with water, because it says that we have a aqueous solution, all right? So let's go and write that down. So we have our hydrofluoric acid, which is a weak acid, reacting with water. And because it's a weak acid, it's not going to fully dissociate, so we have to draw an equilibrium sign here, right? Because this solution, as we'll see, or this reaction can be in equilibrium, because the rate at which the reactants turn into products can eventually equal the rate at which the products turn into reactants. All right, so that's when equilibrium is achieved. All right, and it's a weak acid, so that's why if we were to react HCl with water, there wouldn't be an equilibrium sign here. We would just see one arrow here, because there is no products that can turn into reactants. Because if we had HCl here, right, just a quick refresher, if we had HCl here, it's a strong acid. HCl would fully dissociate. That's why we have one arrow, because this reaction will only go one way. It would fully dissociate into our hydronium and chloride anion. All right. But since we have hydrofluoric acid, it's a weak acid, we don't have one arrow, because weak acids won't fully dissociate into products. It's going to be in equilibrium. So let's go and rewrite it. So hydrofluoric acid will react with water, right, and we'll have equilibrium, where we're going to have hydronium ions produced, hydronium cations, right, because we're still in an acidic solution, because this is a weak acid. All right, and we're going to have our conjugate base, right, so our fluoride anion. Next, our next step is to do our ice table, right? So our ice table represents our initial, our change, and our equilibrium state of a reaction. All right, so let's just write that down. So our ice table, right, stands for initial, change, oops, we already have a C there. It's going to be initial, then change, and then equilibrium. All right, and we'll see how this works in a bit. So let's write our ice table down, and we'll see why we need it. Okay, so we'll see why we need our ice table. Now, what do we have to find out? We have to find out what's the pH of this aqueous solution. How do we do that? Remember, to find the pH, one equation that should pop up in your mind, right, based on our previous acid-base videos, is that the negative log of our hydronium concentration should equal our pH. So that means that we have to find our hydronium concentration, then we can find our pH. All right. So what we have to do is that we already have one part of the problem. It says we have a 1.49 molar solution of our aqueous hydrofluoric acid. That's going to be initially, we're going to start off with 1.49 molar solution of our hydrofluoric acid. So we go and write that down in here. So we start off initially, which is what the I stands for, right? We start off with 1.49, oops, sorry about that. We initially start off with 1.49 molar solution of hydrofluoric acid. And notice ice tables are in molarity, all right? And what will happen is that, so first we have to take the fact that water right, does not affect our calculation of our pH, all right, because water is neutral and its concentration won't change, all right, so we can go ahead and cross that out. That's not going to affect anything, right? So we just have to worry about hydrofluoric acid, hydronium, and fluoride anion. So we start with 1.49 molarity, right? We start with a 1.49 molar solution of aqueous hydrofluoric acid. Then we know, based on our arrows right here, right, based on our equilibrium state, is that hydrofluoric acid won't fully dissociate into their products, right? So that means we know that some of the hydrofluoric acid will dissociate into the product, but we don't know how much. So what do we use to represent something that's unknown? We use a variable. So let's go ahead and use x. So our change is going to be minus x. Now let's pause here and see y again. This is our change. So it's representing what concentration of our hydrofluoric acid is going to change. Well, we know some concentration, some amount, some X amount of hydrofluoric acid will dissociate into products, right? We know that, but we don't know how much. That's why we say 1.49 molar solution of hydrofluoric acid will decrease to some other amount, but we don't know how much, so minus X, all right? That's how much is going to dissociate into products. So what we can write here, right, is that initially, right, our products are zero because our reaction just started. Initially, there's nothing. However, when hydrofluoric acid dissociates into an X amount, we don't know how much, our products are also going to gain that same amount, all right? Because whatever dissociates here is going to be in the product. So we're going to gain the unknown amount of what hydrofluoric acid will dissociate into, all right? So kind of worded that weirdly, but what I'm trying to get at is that we don't know how much hydrofluoric acid will dissociate into the products, so then we write minus X to indicate we don't know how much will dissociate into products, but we know something will. And so that's why we know we're going to gain some products in the form of an unknown variable, an unknown concentration amount. All right, so I hope that made sense. I hope I wasn't too confusing about it. All right, so then our equilibrium section of our ICE table is going to be pretty much just adding these reactions up, right? So this is going to be 1.49 minus X, and this is going to be 0 plus X, which is just X, and 0 plus X, which is just X. So we can go and divide this up, right? This is what our goal was, to get our equilibrium section down of our ICE table. Now we move on, and remember we went over Ka, our acid dissociation constant, or our acid ionization constant. Well, we use that here. That's where it comes in use, is that we write our acid dissociation constant now. What's our acid dissociation constant? It's our products over reactants excluding water, because water concentration doesn't change. So it's not going to affect our Ka. So let's go and do that. So Ka is equal to our H3O plus, our hydronium, times our fluoride anion, conjugate base, over our concentration of hydrofluoric acid, right? That's our acid dissociation constant equation. Now, what I'm wondering is, what do we put in here now, right? Well, we just found it out. We found out that the concentration for H0 plus is X, the concentration for a fluoride anion is X, and the concentration for HF is 1.49 minus X. So let's go and feed those values into this, the spaces for this equation, our acid dissociation equation. Okay, so let's go and do that. So Ka is equal to our X concentration that we saw in our ICE table times our X concentration for our fluoride anion, right, over what was our concentration for HF? 1.49 minus X. So let's go and feed that in. All right, so 1.49 minus X. All right, sweet. Now what do we do? Because we're still trying to find what the H3O plus concentration is so we can find the pH. All right, now that we have this, let's go and simplify it even more and actually multiply the numerator out. So then we're going to get Ka is equal to X squared right? X squared, because x times x is x squared, over 1.49 minus x. All right, sweet. Now our next step would be to find the value of Ka, which we said that we can look up, right? We can look up our Ka values in a table. So it turns out that the Ka value, or the acid dissociation constant, remember if you watched the Ka video, we talked about what Ka represents, right? Represents the acid strength. So the higher the Ka, the higher the value of the Ka, the stronger the acid, all right? Because the more will dissociate into the product. So it turns out that the Ka value for hydrofluoric acid is around 3.5 times 10 to the negative fourth. All right, so let's go and write that down. So the Ka value for hydrofluoric acid, remember, we need the Ka value because Ka represents the acid dissociation constant. We're working with the acid right here, right? Hydrofluoric acid is a weak acid. So the Ka for hydrofluoric acid we said was 3.5 times 10 to the negative fourth, all right, equals, and we'll just finish off what we have here, right? So 1.49 minus x. All right, now we simply have to solve for x. Now we could just straight up start solving here and work with the quadratic equation, right? But we don't want that. We want it to be simple, right? So what we could do right here is we can assume one thing, that x in the denominator is a very, very, very small value, almost close to 0. So if we assume that, then 1.49 minus a very, very, very small value is going to be still about 1.49. So what that means is that now we can write this as this, 3.5 times 10 to the negative fourth equals x squared over 1.49. And now our life's way easier, right? Because now we just have one variable here and we can solve easily. All right, so now let's go and multiply our 1.49 to that side, right? So we're going to have 3.5 times 10 to the negative fourth times our 1.49, and that will get us to x squared, right? And then, so let's go and multiply that out. So if you multiply it out, you should get around the value for 3.5 times 10 to the negative 4 times 1.49 should be around 5.215 times 10 to the negative fourth. All right, and that's all of that's going to equal x squared, and then we just square root, right? So at the end, we're going to get x equals the square root of our 5.215 times 10 to the negative fourth, and it's going to lead to x equals 0.023 molarity. All right, so it's gonna now we have a concentration. But now I'm wondering again, is that what's this random value? How do we use this to find the pH? Because we're almost there. Well, let's go back up and see our ice table. Didn't we say in our ice table that X will represent the concentration for H3O plus, and X also represents the concentration for the fluoride anion? So that means that X is also, that if we have a value for X, that same value is also for the H3O plus value, or the concentration for H3O plus, right? And didn't we just find X, right? So we just found X, so that means we can relate this X value, let's go all the way back up here, to this X value, and if we look a little bit more up, this X value represents the concentration for our hydronium cation. And what did we say our equation was to find the pH? Negative log of H3O plus was the pH. Well, we just found the X value here, right? If we scroll all the way in the bottom, we just found it. So this represents, ultimately, our H3O plus concentration. All right? So now all we have to do now is we'll come here and just do negative log of 0.023 molarity, and we'll find the pH, and then we're done, right? So now let's go over here. So all we have to do now is the last step is negative log of our H3O plus concentration, which is 0.023, which will equal our pH value. So if you go and do that, you'll get the pH equals around 1.64. All right, so the pH is around 1.64 of this 1.49 molar aqueous solution of hydrofluoric acid. And bam, right there, we're done with the problem, and that's it. All right. So that was one example of working with a acid dissociation constant and a weak acid. And so in the next video and in our future videos, we'll continue working with different acid-base examples like this. All right. So I hope to see you guys in my future videos. Again, where I'll talk about more cool topics about biochem, physics, and chem. And don't forget to hit that notification bell and like and subscribe. See you guys later, and stay safe.